Hello everyone. So this week I'll be holding another live presentation of results gathered from Magic the Gathering Arena, this time from a crowdsourced experiment where we're going to look into the probability of going on the play in best of one and attempting to correlate this with the amount of money spent in the game. Before we go to there, I just want to talk about how we're going to analyze the data in that particular presentation. Uh, and so I want to put up this video so that in case you are interested to see how and why we are analyzing the data that way, then hopefully this video will be able to uh, clear that up or to give you a good idea of why that method works. Okay, so we want to guess a number essentially, right? And that number is probability of going on the play. That's essentially the number that we want to guess. We don't know what that number is. Right. So, but what we have is data coming from players, right? So, let's say I'm recording my data. So, let's say on the play. So, let's say I'm going to record my data as 1 if I'm on the play. So, I play a game and then, oh, I'm on the play. So, I'm going to record it as 1. Then, if I'm not on the play, I'm going to record it as a 0, and so on and so forth, right? So, we have this data. And we want to use this in order to estimate this. Okay. Now, suppose that the true data, suppose that the true probability is really 0.5, right? Suppose there's a probability of half that you go on to play. So the data, what should the data look like if this is true? So the data can look something like this. So I'm going to write a function here. So rand is a function in Excel that will give you a number from 0 to 1 on a uniform distribution, meaning that any number from 0 to 1 is equally likely to occur. So if this number is less than 0.5, I'll say I'm on the play. Otherwise, I'm on the draw. Okay? And so this function effectively generates us the numbers that are going to happen if this is indeed the truth. So therefore, one particular set of numbers, because we said at least 15 trials, right? So one particular set of numbers that a player might get if this was true, if indeed 0.5 is the probability of going on the play is this. And what is this one? So how do we try to estimate this truth from this data? So we can estimate it by just counting the number of times that we see a person went on the play. So just counting these ones, so summing up these ones essentially, and then dividing them by the number of times that the person played. So in other words, our estimate is just the sum, right, of these numbers, the sum of the ones rather, which of course will be some, only the ones will sum up because your zeros will not add to the sum, divided by the number of trials, in this case 15. But we could use the function count to do that for us. So I'll press enter. And so this is going to be our estimate for this set of data, which is far from the truth, right? This is far from the truth. The truth is 0.5. But since we only have a small sample size, 15, then it's likely for us to get something like this. And that's fine. That's okay. Okay, I'm going to show you later on. This is okay. Okay, so this is far from the truth. We don't want to base our entire assumption, our entire conclusion based on this number. Okay, but what we can do is we can construct a confidence interval of our estimate. So a confidence interval will provide you with an interval for which you can have a certain level of confidence that your target is in that interval. How do we construct that confidence interval? Where there's a formula. So we want first to compute for the standard error. And the standard error, this is going to keep changing. So I'm going to I'm going to stick to this. Right? I'm going to stick to 0.6. So meaning, let me just copy this and paste the values. This time it's not going to change, right? So I'm going to change it back later. But for now, we're going to stick with this data just so it won't move around. So we want to compute the standard error. That's the square root of this number multiplied by 1 minus that number divided by the sample size. And you can look up these formulas. Alright, so that is our standard error. Alright, and then what we want to do is to establish or to identify a level of confidence that we want. So let's go for a 95% confidence. So that will provide us with a constant for us to use for the confidence interval. If it's a 95% level of confidence, 1.96. All right, and anyone who's taken basic stat class would remember this number, hopefully fondly, as one of the numbers you want to memorize so that you won't have to look it up in the table so often. All right, so now that we have our standard error and our level of confidence, it's now time to construct our interval. So that's just a matter, so this is our interval. That's just a matter of getting our initial estimate, right? Our initial estimate here, and then subtracting 1.96 multiplied by the standard error. So that will be our lower bound, and then our upper bound would be the opposite. You have your estimate and then plus 1.96 multiplied by the standard error. And so this becomes our interval. This becomes our interval. And so what do we mean by that? We can say that we are 95% confident. We are 95% confident, and that is a loaded term, what we mean by confidence. I won't probably, I'll go into a bit more detail about that. So we're 95% confident that our target is in this interval. That's what we're saying. We're 95% confident that our target is in this interval. So in this case it is, right? Our target is 0.5, and clearly 0.5 is in this interval. Okay. However, if we're looking at the interval, it's not a very nice interval. So basically it's telling us that the probability of going on the play can be anywhere between 35% to 84%, which does not help us by much, right? So what happens is, so we need a bigger sample size. So by the way, what we mean by confident, I did say I was going to expound on it. So what we do mean by confidence here is that if I repeat this experiment 100 times, what we mean by 95% confidence is if I repeat this experiment 100 times and I construct 100 different confidence intervals, then 95 out of 100 of those confidence intervals will actually contain my target. So that's what we mean by confidence. That's a bit of a formal definition of what confidence means. So if we increase our sample size, we will be able to get a much tighter confidence interval. Okay, a narrower interval, and so that will be more useful to us. So that's what I'm going to demonstrate here. So I'm just going to get back that formula. Right, that was the formula, right? So let me increase the sample size. Let's say just to 100 first. So 101 to make 100. So we started at 2. Started at 2. All right, so as you can see here, our estimate is 0.53. We have a much smaller standard error this time. So of course, you can see that that's going to happen as we increase the sample size. The standard error is going to decrease because the sample size is in the denominator of the standard error. So as you can see here, we are now saying that well, the probability of going first, of going on the play, is anywhere between 43% to 62%. So this is a much smaller, a much narrower interval than what we had the previous time. And if I change this, it's still going to be narrow. Although, as you can see here, this one does not contain the truths, right? So this one does not contain the truth, because the truth is 0.5, but it's not contained in this interval. And that's what we mean by 95% confidence. So sometimes we'll get this, but that's actually not. So this out of 100 samples. Out of 100 samples, we get this. It does not contain our truth, right? But this does not happen very often. This does not happen very often, right? As you can see there. Okay, so how about if I increase it more? So here we have 100 samples. How about if I increase it some more, say to 500 samples? We actually get to much higher number of samples from on the experiment. It's 600 something samples. All right, so if we have that, as you can see here, so the interval becomes even narrower. Right? So it's not going, we're not getting any of the 0.3s anymore. Right? And if I increase it some more, to 1,000, then we're going to come closer and closer to a narrow interval. So the interval is just going to narrow further, and those intervals are going to each of those intervals are still going to contain our target. Okay, so this is why this is one of the ways by which we will be estimating the proportion of going on the play. We are lumping together, we're going to lump together the data from each of the participants. So note that we require that each participant have 15 games, but some participants have actually contributed more than 15 games. Many have contributed more, some have contributed a lot more, like 50 games, or some even 100 games. So we are confident that when we use those estimates and we pull them together, that we will be able to get a good estimate of a probability of going on the play. By the way, so suppose that the true probability is not 0.5, but it's actually 0.3. Suppose that's the true probability. So let's see if this is still going to be able to capture that. So of course I have to change this. Instead of 0.5, now I want 0.3, right? So this is the data that I can see. And as you can see here, well, this is an odd, so of course it's going to change. And this is an outlier. Rather, one of the times out of the 95, out of the 100, where your confidence interval does not contain the 0.3. But if I change this to another sample, now this one contains 0.3, and it's much lower than the previous one where the truth was 0.5, but now the truth is 0.3. If I do that again, as you can see, these estimates will contain the true parameter. As you can see, over and over again, the intervals are narrow enough for us to make a suitable conclusion that indeed something weird, if this is the truth that we're going to get, then there's something weird is going on, because we shouldn't be getting these numbers, and these numbers would indicate that we are going on the play fewer times than 50% if we get an interval like this from our results. But we're not going to get an interval. We didn't get an interval like that. Okay, so another thing is, instead also of doing it this way, right? Instead of just lumping them together, we could also look at the individual values. So each person contributed, let's say 15, right? Each person contributed 15. And some people contributed more than others, and I'll get to that in the actual study. So let's say this is participant 1, right? And let's say we have several participants, right? 2, 3, 4, 5, 6, 7, 8. That's just for purposes of simplicity. I'm going to leave this at 8. participant 1. So now let's put in some data here. All right. So is this still 0.3? Wait. There. Okay. Okay, so this is, oops. So this is the participants. We have 8 participants, so I'm going to make it 10 participants. Of course, we have at least 30 already. We're past 30 actually, which is the number that I wanted to get. All right, let me delete this extra one. So for each participant, we're going to calculate still the number of times that they went on the play. So that's still the sum of this, divided by their total games, which is 15 for all of these in this example. But like I said, in the actual data, there's more than 15 for each. So as you can see here, there are different numbers for each of them. Oh, sorry, this is still at 0.3. I have to change that to 0.5. There. That's why the numbers look weird. Okay, so here the truth is 0.5. Okay, so here the truth is 0.5. So each individual will be submitting data that essentially looks like this, right? So this person went 73% on the play, whereas this person only went 40% on the play. And this person only went 30% on the play. So as you can see, it's very widely different. But if we get the average, so what we intend to do is we have all of these individual data with differing number of times that they played, but we're going to take the average of them. All right, we're going to take the average, and that's going to be our estimate. Okay, so as you can see, even if some of them have high values, some of them have low values, of going on the play, when we take the average, it's the same effect as what we're seeing here. It's the same effect. That is, we will be able to consolidate that data into something that is closer to the truth. So in this case, that's 50%. Okay, so if I press, of course, it will differ by a bit, but as you can see, it's not differing by much. Okay, and we can also construct a confidence interval for this one. Okay, so the formula is different. We will need the standard deviation. So we still need the standard error for the estimate. So that's going to be the standard deviation of these numbers divided by the square root of the sample size. So the sample size here is not 15, but it's the number of numbers that we have here. So 10, but I'm just going to use count. There. Okay, so that is the standard deviation. As for determining confidence, we will not be using 1.96 as we did previously, because this will be a slightly different distribution. We will need to make use of the t-distribution here. So if we want a 95% confidence interval, I will need to get, instead of 1.96, I need to get a constant for the t-distribution, probably 0.05. Degrees of freedom is not some sample size minus 1. So if we let the sample size be very, very large, it will eventually get to the same number, 1.96. But in our case, we only have a sample size of 10, so degrees of freedom is 9, 10 minus 1. And so the value that we need is 2.26. So with that in our estimate, we can now construct our confidence interval, which is still essentially the estimate plus minus the standard error multiplied by this value, it's lower bound, and then the upper bound is the estimate plus the standard error multiplied by the confidence. All right, so here, as we could see, we also capture the truth. So the truth is 0.5, and it's still also going to be included in that interval. So if I change the interval, so as you can see, the interval is a bit wider, right? Because we are using a t-distribution, and so we have a larger factor that we're multiplying. But this is for sample size 10. In our actual sample size, we have sample size that is over 30 already. So you can see a considerable decrease of this when we apply this to the actual data. And of course, if the truth is really that people go on the play only 30% of the time, right? If I change that to 30% of the time, let's see if we can still capture it this way. We will still be able to capture it. So if we do get a result that looks like this, then we will know that something is amiss. That is, we will know that the algorithm is putting or making people go on the play fewer times than 50%. So we will be able to detect that if that is the case. So that's it. So that's this short video on the method that we will be using on the study that I'll be presenting later this week. So I hope that this was I hope that this was informative, and I'll see you this week when I present the results of the studies.